Yes, I can do that, I guess. Just having trouble with my Zoom. Okay. All right, I think I can do that. Can you hear me?
Yes, that's fine.
Should we then start or
Yes.
take a break?
No, I think we're ready to start. The only thing is if you want to show both the CompuCell and the PowerPoint, you have to make sure that the mode when you start the PowerPoint is correct.
Sure.
I set it for deck 3.5, but you need to double check.
All right, so let me actually share my screen. Desktop 1, sure. Can everybody see my screen? I hope so. So let's go back and start the presentation.
Not in PowerPoint.
No, I'm having a hard time hearing you.
You're going to do it in Google Slides or in PowerPoint?
I think I'll do it in Google Drive. The Microsoft Office is just unacceptably slow for whatever reason on my computer.
Okay.
And actually, this Google presenter does a very good job of rendering PowerPoint presentations. So
I'll get out of your hair. Let you take over. This is Maciej Swat. He's the one who actually wrote CompuCell 3D. So if you have any questions about how it works internally or issues or suggestions, he's the person to talk to. So I'll turn it over to Maciej for our last presentation of the day.
And I have 1 hour, right? Roughly.
Yes, and then if it runs over, you can use tomorrow.
Sure,
morning.
yeah, exactly. All right. So I hope everybody can see my slides. If you don't see my slides or if something is missing, please let me know. All right, so let's start the discussion of a little bit of theory behind CompuCell 3D. So CompuCell 3D implements Cellular POTS model. So this model has been developed by James Glazer and Francois Grener. And in this model, you probably saw it already, but so I might be repeating some information here, but it doesn't hurt to repeat that so that it sinks better. So this model essentially represents single cell as a collection of pixels on the lattice. And lattice can be regular or irregular. So for example, here, we have a situation where we have 4 cells, right? We have purple cell, orange, yellow, and green. And we have also this 5th cell, actually, that is called medium. And by now, you probably know that medium is also a special cell type. And the only difference between medium and other cell types is that you cannot constrain the volume of medium as implemented by default in CompuCell 3D. So the whole formalism of Cellular POTS model is physics-based. It has its origin in statistical physics, and it uses energy formalism to describe cell properties. So you have already learned that by introducing different constraints, you can have cells exhibit different behaviors. So for example, cells can grow, they can shrink. So that would be modification of volume constraint. They can stick to each other. Modification of, you do that by modifying contact energies, and so on. And there are many other constraints, energy terms that we can use, and I will go over some of those. So the simulation is stochastic, it's not deterministic. That means that every time you run CompuCell simulation, you will start with slightly different seed. And that means that your results in principle can be a little bit different from simulation to simulation. There is, of course, a way to set random seed, but typically what you're interested in, you're interested in generating ensemble of simulation outputs and then doing some type of statistical aggregation at the end, if practical. You know, sometimes the simulations are quite costly and they take quite a long time, and that this is when you probably will stick with very low number of repeated simulations to draw some conclusions. The nice thing about POTS model, it's very simple and intuitive. I mean, we are not writing anything complicated. We are not going beyond, you know, second order equations when we implement constraints. We, you know, take quantity and we square it. So that's as far as mathematical complexity goes. Typically, we can run up to 10 to the 5th cells on a single CPU. The simulation will run a little bit slower, but it's achievable. Cellular POTS model is used by many groups around the world. The only issue that you have to be aware of is that time has to be converted from simulation unit to physical unit. And typically what you do, and I think, I'm not sure if you covered it already, or maybe in the following days, people will cover that. Typically what you do, you look at mean displacement of cell in your experiment, and you try to match that to the mean displacement of a cell in your simulation, and then establish this matching, and I'm not going to go into details, establishes essentially relation between your Monte Carlo step and physical time. And Cellular POTS model has been implemented by several software packages. So I'm going to list a few of them that are most popular. So CompuCell3D, there is Chase implementation, Simune, Morpheus, and Tissue Simulation Toolkit. I think it is probably fair to say that CompuCell3D and Morpheus are two main implementations of Cellular POTS model. All right. So let's. So this is typically how we go from experimental image into a conceptualized view of cells on the lattice. So we have a microscopic image of somites. We represent them. We represent the cells that we observe on the microscopic image as spatially extended domains. So CompuCell cells, right? And then if we zoom in into this region, we can essentially see how cells are being laid out. So things to remember is that each cell can occupy many lattice sites, and each cell has unique ID, unique index, right? So in simulation, you know, if you iterate over a list of cells in CompuCell3D, each cell will have different cell ID, right? So for example, and then also each cell has a different type, has a type actually assigned to it, right? So in this particular image, I have 4 cells and they all have different type, right? So we have cells of type purple, if you let me make this, you know, simplification by calling type purple, but I think this is convenient to use for this presentation. We have orange cells, and there can be many cells of type orange, right? So if we look here, there are literally many cells of type orange. So this is something to remember. Cell ID and cell type, those are 2 different quantities characterizing cell. So the configuration of cell fields, so the way we do simulation is that we randomly perturb lattice and we compute energy that is associated with each lattice perturbation, right? So for example, the key concept in Cellular POTS model is contact energy. And let me go back here and let me actually explain how contact energy gets calculated. So contact energy gets calculated by essentially summing contributions between interfaces that belong to different cell types. So with each interface, right, with each interface of a single pixel, we associate, we essentially add contribution to contact energy by counting those interfaces. So here we have 1, 2, 3, 4 interfaces between purple cell and a medium, we have 1, 2, 3 interfaces between green cell and purple cell, and so on. So if you want to compute total contact energy for all the cells, we have to sum all those interfaces, right? So that's how CompuCell computes energy. And if we go to the next slide. So essentially the idea is to make those tiny perturbations compute energy that is associated with every single pixel copy attempt, and then accept or reject those perturbations. So at each step, essentially that's what's happening. And I'm gonna walk you through the key concepts. So let's go to a picture that actually visualizes what happens during several pixel copy attempts. So for example, let's assume that this is our lattice configuration. So first thing we do, we randomly pick a site on the lattice, and then we pick a neighboring site, a close site, right? Where we want to copy the pixel from the source pixel into the destination pixel, right? So here, for example, it happens so we picked a pixel that belongs to blue cell, and we try to copy blue cell onto another pixel that belongs to the same cell. And this pixel copy doesn't make sense because it doesn't change, it doesn't perturb lattice. That's why I call it invalid pixel. So if CompuCell encounters such a situation, it will essentially say, okay, let's skip this, let's don't calculate anything, let's move over to the next pixel copy attempt. Okay, so let's do that. So we pick random site, it belongs to green, to the cell that is green, and we try to extend this cell and copy its pixel into neighboring site, which happens to belong to this orange pixel, orange cell. So what happens here? Well, first of all, if we accept this pixel copy, the green cell will become bigger, right? If we have volume constraint, the volume energy will get affected. The orange cell will become smaller, so the volume constraint for orange cell will get affected, right? And then, of course, there will be some change in the contact energy, which we'll have to take into account. So essentially, we propose this pixel copy and we compute energy before and after. And then if the change of energy is less than 0, we accept this pixel copy unconditionally. If the change of energy due to proposed pixel copy is greater than 0, we accept this, this pixel copy with the probability that decays exponentially using this formula. So it decays exponentially where delta E is in the numerator and T is this membrane fluctuation, cell membrane fluctuation parameter or temperature. So, so looking at this algorithm, you can tell immediately that essentially what CompuCell does, it minimizes the overall strategy of CompuCell is to perturb lattice and move the overall cellular configuration in such a way that at each step, on average, we minimize the energy. All right? So that's what happens. And at each point, I want to make sure that, I want to emphasize that at each point, whatever configuration, whatever perturbations to the lattice we make, we always try to satisfy the constraint. So for example, if there is a volume constraint, this energy formalist will make sure that cells will not deviate too much from the target volumes, and so on. So this is one pixel copy attempt, right? So in this case, we accepted it. There can be another pixel copy attempt, right? We can copy the pixel not just to the first nearest neighbor, but also to second nearest neighbor. and in this case, we can accept this. And it's interesting to look at this configuration because, in fact, and this can happen in CompuCell, this may lead to cell fragmentation. So for example, it's not hard to imagine that after next, so this cell is almost fragmented. So this pixel is essentially pretty much detached from this cell. And it can happen for a certain range of parameters that the cells can actually get fragmented, and we'll go over this, the simulations like that. And the idea is to apply constraints in such a way to avoid fragmentation, because that probably makes most sense. So let's look at, so I was talking a lot, about how those pixel copy happens. So let's really look in detail what really happens in a single pixel copy attempt. So this will give you better understanding of what CompuCell does under the hood. All right, so let's assume that we have simulation. We have simulation where we only have two terms. We have contact energy, and we have volume energy term, right? If you look at this formula, it looks a little bit scary, especially this delta function. But what this delta function does, what this parenthesis does, is it makes sure that you don't count interfaces between pixels that belong to the same cell. That's all there is. So don't get scared by this term. Okay, so before pixel copy happens, when I compute energy of the system, I count it here. So there are 18 pixels that belong to the green cell. Okay, so the energy term associated with volume constraint for green cell is 18 minus whatever target volume for the green cell we have, squared, multiplied by lambda green. For orange cell, there are 15 pixels. So the energy term is this one. And then there are contact energies here, okay? The important thing is that due to the pixel copy, what's gonna happen is that those two interfaces between green and orange cell will be lost, right? But they will be replaced by two interfaces here. So essentially, if we compute change of energy, of contact energy due to only contact energy due to this pixel copy, there will be zero change, right? So the only change of energy will come from volume terms, right? And after so if we consider situation after pixel copy, if we were to accept this pixel copy, this will be the energy term for this system, right? So then what we have to do really is subtract energy after from energy before, right? That gives us delta energy. And then if this delta E is less than 0, we will accept this pixel copy. If it's greater than 0, we will accept it with a certain probability that's less than 1, right? All right, so that's essentially what happens with the single pixel copy. So this is essentially a recapitulation of what I have just said. So once we have delta E, we use this rule to compute probability, and you probably know by now, how to accept pixel copy with certain probability. Essentially, what we do, we generate random number between 0 and 1, and if this random number is less than computed probability, we will accept the pixel copy. All right. So that brings me to the slide where I'm listing some, not all, but some energy terms that are available in CompuCell 3D. So we already covered volume constraint. By analogy, when you have volume constraint, you can also create surface constraint. You can replace the word volume with surface. You can have lambda surface, and this is surface minus target surface, right? I haven't listed it here. You can have chemotaxis, right? So you can introduce pseudo energy term, which will make cells chemotact up or down the concentration gradient depending on the value of chemotaxis lambda, if it's positive or negative. You can also implement external potential or force. So essentially, you can apply by adding energy term where you look at the displacement of the source and destination pixel. You can essentially simulate a force. You can have you can put constraint on inertia tensor, and that way you can elongate or shorten the cells. You can have adhesion that we know, and it's worth noting that adhesion does not have to be, the CompuCell gives you opportunity to apply adhesion between not just cell types, or specify adhesion not just between cell types, but specify adhesion between different individual cells. And I think tomorrow, Julio will cover that. And so on. So there are many terms that exist already in CompuCell. You can also write your own energy term. And the nice thing about CompuCell is that if you want to include your energy term, all you have to do is write a plugin. And we have a tutorial that teaches you how to write a plugin. So in that way, when you write a plugin, you don't have to modify too much of the code. You just write a simple module, that's a standalone module that you can then contribute to CompuCell, or just keep it for your private purposes for your research and then use it. So in that sense, CompuCell is quite extensible. So let's go over some terminology that probably you have encountered, but let me actually go over it again. So CompuCell has those, CompuCell simulation can be thought as a simulation taking place at two scales. So there's fast scale and slow scale. So at the fast scale, we are talking about pixel copy attempts. So we discussed this essentially. So pixel copy attempt is this micro unit of operation of CompuCell 3D, right? And it happens, and we are doing plenty of those pixel copy attempts. So each Monte Carlo step consists of, typically consists of number of pixel copy attempts that is equal to number of lattice cells, okay? And at this fast scale, we typically use plugins that compute effective energy, okay? So in addition to plugins that compute energy, we have also lattice monitors. So lattice monitors are CompuCell modules that make sure that, for example, center of mass position, that volume, that surface of the cell, lattice configuration takes place. So those are the modules that are typically written in C++, both energy terms and lattice monitors. And the slow scale, we're talking about Monte Carlo step. So Monte Carlo step is, as I mentioned already, a unit of time, and typically we call one Monte Carlo step after we try to do number of pixel copy attempts that is equal to number of lattice sites, right? And then in between Monte Carlo steps, we run modules called steppables, right? So at the end of Monte Carlo step, we call a series of modules that are typically written in Python, and they are called steppables, and most of those modules perform some type of customizations, right? So for example, you can adjust cell types in the steppable. You can change target volume, lambda volume. You can have cells. You can read the chemical field. You can change chemotaxis properties, and so on. So those tasks are typically and most conveniently done in Python. I want to mention one thing, that even though we typically use Python, because Python is super fast to develop, you can also write steppables in C++. In fact, if you're really struggling, if you notice that your simulation is slow because your steppable is written in Python and takes too long, you can rewrite it in C++. Of course, there are ways you can optimize things in Python, but really, I mean, going to C++ is also an option, and I want you to be aware of that. So this is pictorially what happens, how the simulation looks like. So we do Monte Carlo step. Let's assume that we have 100 by 100 lattice, so 10,000 pixel copy attempts. And after each Monte Carlo step, we run steppables. All right. So I hope this is clear so far. Okay, so this brings us to the question of nearest neighbors in CompuCell 3D or any POTS model, the notion of nearest neighbors. So if I go a few slides back, maybe I don't have to go. I'll just tell you. So you remember that when I was when I was talking about pixel copy, I was showing you that you can copy this center pixel into its nearest neighbor, or you can copy it on the diagonal, or you can even copy it even further. And there is a setting in CompuCell, and typically it's called neighbor order. So if you see neighbor order 2, that means that you allow pixel copy to take place between first and nearest and second nearest neighbors, right? So essentially, the concept of nearest neighbors is quite simple. You pick a pixel, and then you look at, you categorize nearest neighbors, you categorize neighboring pixels based on their Euclidean distance. So for example, this center pixel has 4 nearest neighbors, right? They are here. It has 4 second order nearest neighbors, right? They are those guys on the diagonal. Then it has 4 third order nearest neighbors. Those are those guys with 3, and so on. And those are the distances, okay? In practice, we use, between 1 and 4 nearest neighbors. One thing that you have to be aware of probably is if you want to avoid lattice anisotropy effects, it's a good idea to keep the nearest neighbors to essentially use higher values, 3 or 4. And there are 2 things that I have to emphasize here. So there's a separate setting for how far a pixel can jump in a pixel copy attempt. So this nearest neighbor value is specified in the POTS section. There is separate nearest neighbor specification that we use in contact plugin. So typically, the important thing is to make sure that this specification of nearest neighbors in contact plugin is actually high, right? And what does it mean? That means that when you compute contact energy between pixels, right? Previously, I told you that, and I consider the simplest case, that we only count interfaces between, cells of different, we count only interfaces between different cells. So I would say that then you would count interface between this blue pixel and this yellow pixel and this pixel and that and yellow, right? But if you increase this neighbor order, you would also include interfaces between other pixels. So you would go to second and third nearest neighbor if you actually change contact energy nearest neighbor setting to be 3. So that means, so what that does in practice, it makes sure that, for example, if you're trying to create rounded cells, that your cells will look more like a circular cell rather than a cell that looks like octagon, and that essentially can happen. So, for example, if you imagine in CompuCell, if you want to create big circular cell, right, and if you use low neighbor order in contact energy, most likely you will end up with octagon. If you want to have truly nicely circular cell, sometimes you might have to go to 20th nearest neighbor. So that's something to be aware of. Of course, that will depend on the size of the cell, but something to be aware of is that whatever neighbor order you choose, CompuCell will actually perform computations for you. If you use really high neighbor order, the computations will obviously take a little bit longer. So another thing to be aware of. In addition to Cartesian lattice that we are mostly familiar with, CompuCell also has option to use hex lattice. The hex lattice is this honeycomb, right? This is in 2D. In 3D, hex lattice is a little bit unintuitive, and I can tell you that it uses rhombic dodecahedron as a unit, and the properties of the 3D lattice are a little bit unintuitive to grasp first. So essentially in 3D, the lattice structure repeats every 3 layers, right? Here, the lattice structure in 2D repeats every 2 layers, right? So those honeycombs, right? So those hexagons are shifted by half of the distance from row to row. One thing to be aware of when using hexagonal lattice is this. In CompuCell, each pixel, whether this is a Cartesian pixel or hex pixel, whether this is 2D or 3D, has a volume of 1, right? If we use this volume constraint of 1, that means that the distance between hexagons is not 1, really. And also, the length of the hexagon is not 1. And we have a write-up about hexagonal lattices on our website. So if you are looking for those conversion factors, it's all there. And finally, it may happen that some functions may not work properly on hex lattices. It shouldn't. I mean, it's not a large number of functions, but it may happen. So just something to be aware of. All right, so we covered the theory behind CompuCell, and I think it's a good idea to do exercises right now. So the way I structured the rest of this talk, and I will not finish it today, but I will finish tomorrow morning, is the following. So each simple exercise will have a simulation associated with it. So for example, this is our first simulation. It's called single cell example _1.cc3D. I'm gonna get out from the presenter mode, and I'm gonna go to the CC3D course, the student materials on the Google Drive. If you go to CC3D theory, there are several simulations here. So when we talk about this first simulation, single cell example, I want you to grab the zip file and open it into Edit, or if you have version 4.2.3, you can open it directly in CompuCell 3D. So let me actually do this for you. So let's do this exercise together. So the goal of this exercise, let me actually explain what the exercise is about. Going back to presenter mode. So the goal of this exercise is to start with a single cell. So this is our initial configuration. And we will only use contact energy, right? And we change contact energy coefficients to be negative. And if you run this simulation, after a few Monte Carlo steps, you will see that the simulation takes entire lattice, takes over the lattice. If you look at the output here, you will see that this is just a single cell, because there is, if you look at the cell inventory output, it says there's one cell only, right? So the question is why? Can you take a few seconds and think why with this setup, when we have only contact energy, no volume constraint, and energy coefficients are negative, why does single cell explode and take over the lattice? So think about it, and in the meantime, I'll show you how to open things into Edit, which probably you know by now. All right, so let me actually pause this. So I'm gonna I'm going to go to the Google theory. Sorry, CompuCell CC3D theory folder. Click download, and I'm gonna download this. Yeah, it already is here. I'm gonna save it. And then when you open this simulation, workshop, into edit, you can select zip folder, and CompuCell and Twedit tells me, displays this message, could not create default unzip folder. Perhaps it already exists. It does exist because I checked just before this presentation that the simulation runs. So I'm gonna hit OK, and CompuCell will give me another dialog where I can select, I can specify new folder, and this new folder I'll call single cell demo. Hopefully for you, since you have not created, you have not used this simulation, you will not have to go through that step. Create, and I have to hit open, and my simulation is open here, right? So if I run it, let's see if it runs. I hit CompuCell player open. Okay, so it was too fast, and I zoomed. So the settings were such that you essentially were zooming at the fragment of the simulation here. So I unzoomed. You can hit R. If you type R, I think it should. Sorry, it should reset the view. So let me stop the simulation and let's start over. Let's step. Have we done exercises? No. Maybe I'll just do this. All right, so I'm doing essentially, let me zoom in a little bit. I'm doing a few Monte Carlo steps. And you can see this cell spreads like spaghetti. So why does it happen? Well, let's go back to the presentation. There's an answer there. All right, so let me jump to the presentation. So this is, by the way, this presentation has also code highlights. So I just want to show you that the code is really simple. So this is standard CompuCell simulation where we have just one cell type called condensing, and the contact energy between medium and condensing are set to -10. I don't have any initializers in XML. I'm creating a single cell that is 1 pixel wide in start function of the steppable. And that's the syntax I'm using. So the reason why this cell occupies the entire lattice is that we are essentially, the CompuCell minimizes energy. If each interface between cell and medium contributes -10 units of contact energy, how would you minimize the energy? You would essentially create as many interfaces between medium and cell as possible. And that's why you did this spaghetti or labyrinth pattern, right? Because each single interface that you're looking at contributes -10 units. So if the more -10s you have, the lower your energy. So that's why you observe this pattern. All right, so let's switch gears and let's go to the next exercise. Okay, so let's do the opposite exercise. Okay, let's start with single cell, but this time we are going to use positive energy coefficients, right? And the question is, why does the single cell disappear? And I'm already giving you an answer. So you're free to go ahead and open this simulation. It will be a very quick simulation because the cell will disappear after a single Monte Carlo step. So I'm gonna save ourselves some time and skip this step. But essentially, this is the answer. So before my pixel copy attempt, I had 4 interfaces between cell and medium, and each interface contributed 10 units of energy. So I had my total overall energy, because I have only contact energy, was 40 units, right? Sorry. And if I get rid of the cell, if I override this pixel belonging to a cell with pixel belonging to medium, I will go from 40 units of energy to 0 units of energy. So that's exactly what CompuCell does. And hopefully this gives you an intuitive feel why, what contact energy does really. What type of role does it play? Okay, so this was exercise number 2. And so this is the listing. Again, nothing fancy. It's the same listing as before, except I changed the contact energy here. So let's go to another exercise and another case where we will actually add volume constraint. So our Hamiltonian will have contact energy and volume constraint. So if we are adding volume constraint, all you have to do in XML really is to specify, is to tell CompuCell, hey, I want to include volume constraint. And you do this by including this syntax, plugin name equals volume. When you don't specify any, when you leave it like that, what you have to be aware of is that with such specification of volume constraint, you have to specify volume constraint parameter, lambda volume and target volume individually for each cell. And that's precisely what we are doing in Python. Okay? So in Python, what we are doing here is we create a cell. Okay, so I'm creating a new cell here, right? So self, new cell. So this is a function, a standard CompuCell function that it's in every stepable. And I'm assigning this cell to, I'm storing this cell in a variable called cell, okay? Then in the next line, I'm taking the cell field and I'm populating pixels between 100 and 101 in X direction and pixels between 100 and 101 in Y direction with a cell. So essentially I'm laying out cells on the lattice, right? And here in this particular case, I'm only assigning single pixel because because I'm going from 100 to 101. If I went from 100 to 110, my cell would be, in both directions, my cell would be a square, 10 by 10. But here it will end up being a pixel. The next step is I have to assign lambda volume and target volume individually for this cell. Since I have only one cell, that's what I'm doing. So I'm assigning target volume to be 25 and lambda volume to be 5, okay? And let's run this simulation. So let me jump out of the presenter mode. Let me go back to, sorry. Go back to the screen. I'm gonna download this simulation. And this time, instead of actually opening it in Threaded, which I can open it in Threaded, that's easy. So I can maybe close this. I want to open it directly in CompuCell3D now. For you, if you're using older CompuCell3D before 4.2.3, this feature might not be available, but I'm going to show you what will be available in the next version. So, open simulation, workshop. Come on. I wonder if I downloaded to the right place. Download. As it is. Interestingly, I downloaded into wrong folder. Let me actually go back and re-download it properly. Download. Okay. All right, so let me open demo 3. Oh, it takes time. Zip. All right, so let me reset the view. So this is our single cell. I run it. So after a few Monte Carlo steps, let me zoom in. This is how my simulation looks like. The question is why? Why do I have this cell that doesn't occupy entire lattice, but it's still fragmented? So I have volume constraint, right? So let's go back to the presentation. Let's go back to the presentation mode. So the reason why we're ending up with this pattern is that yes, we've added volume constraints, so we make sure that our cell will not grow much beyond those 25 pixels, but still our energy, contact energy is negative, right? So it's still, in order to minimize energy, the CompuCell will essentially create fragmented cells whose total volume will be close to 25 pixels as we specified, but in order to minimize energy, it will create as many interfaces between medium and the cell as possible. And the reason why it's doing so is because such interface lowers the energy. So that's why. So let's do the final exercise for this section. It's called single cell example 4. Okay, and I'm not gonna run it. I'll just tell you what happens here. Or maybe we'll run it. Essentially, we use the same setup. We have two energy terms, contact and lambda volume. So there is really nothing interesting going on in Python. The only thing I did here is I increased the initial cell size from being 1 pixel to 2 pixels. And this is to prevent cell from randomly shrinking. So this time our contact energies are positive. And if I go to, the final result, you will see that if you run the simulation, your cell will look more or less like the cell that you would like to see. It will have volume of, roughly speaking, of 25 pixels or close to it, and it will be all rounded. So why does it happen? Well, we understand why 25 pixels, right? Because volume constraint makes sure that we don't go beyond, much below or much beyond 25 pixels. And the reason why this shape is so like more circular-like shape is because when contact energies are positive, we want to minimize, by minimizing, one way to minimize energy is to lower the number of interfaces between cell and medium. And this is precisely why we get this shape. So, so those 4 exercises essentially are all the exercises I wanted to do, or not really exercises, but small, simple simulations. Those are the 4 simulations I wanted to do in order to illustrate so like the basic principles of how to think about contact energies, what contact energies do, and what volume energies do, and what is the interaction between those 2 energies. And in the next few simulations that I will go over, and probably not today, but I'll walk you through several steps where we'll take this simple simulation that includes only 1 cell, and we will build a model of a vascular tumor. So that's the goal for tomorrow. Since I have 5 minutes left, maybe let's talk about one simple simulation, and we'll stop there in really 5 minutes. So I want to talk about how do we want to build this tumor simulation. So first of all, what would this tumor simulation involve? I mean, no, when we're talking about tumor models, we definitely want to implement cell growth. So the question is, how do we grow a cell? First of all, let's ask a different question. What type of energy terms we want to include? We clearly want to include contact energies, right? Because contact energies is an essential term that essentially allows us to control a shape, and it's a biological interaction that pretty much drives quite a lot of patterning in biology. So in pretty much every CompuCell simulation, you need to have some sort of contact energy included. And here we are using this standard contact energy formula. And we want to have volume, right? Because we want to control volume of the cell. So the question is, how do we implement cell growth? Well, a simple way is to modify. So in start function, we specify target volume and lambda volume. But if we want to implement growth, what we want to do is in step function, we can increase target volume by some number of some numbers. So here I'm choosing 0.2. One thing I want to make sure that you understand is that this target volume and lambda volume, they are floating point numbers, right? So they don't have to be integers. So here I'm increasing target volume by 0.2 units, okay? And again, that depends, the increase depends on actual parameters, biological parameters that you would use. But here, for this demonstration purposes, I'm using this number. And this is essentially all it takes to have your cell grow. So let me exit this screen, and let me go to the drive and open up cell growth simulation. So I'm going to download it. I really hate the way Mac does. Am I in the right folder? Looks like it is. Let me make sure. So I saved cellgrowth.1. This is the simulation that was specified on the slide. And I'm gonna stop the previous simulation. Do open. Workshop. Like this. I'm gonna open the zipped folder. Again, if you don't have the latest CompuCell, you will have to open it in to edit and then open it in Player. Two-step process, but I'm gonna save us some time. Yes, I'll unzip it there. And this is my simulation, right? So as at each Monte Carlo step, I keep increasing target volume of the cell. And as a result, my simulation as a result, my single cell, the only cell that I have, keeps growing. So nothing is happening. So I'm gonna stop presentation here, and tomorrow we'll learn how to do mitosis. I'll walk you through the code explaining the mitosis, and then yeah, we'll go on and build a vascular tumor simulation. So I think I'll stop now, and I think that's a good time to stop. And if you have any questions, if anybody has questions, let's go over them. We have 3 minutes. If not, I'll see you tomorrow. So. Do you have any questions? Not, I'll hand it off to James. Sure.
Okay, thank you very much, Maciej. Appreciate that. So tomorrow's the last day of our workshop, the day after we start the hackathon. So please do let us know about your hackathon interests and plans so we can help plan that and get that set up to start on Friday morning. Tomorrow we will cover the last bits of the infection and immune response model that TJ and Joshua have been showing you. Maciej will cover the tumor model, and there'll be some demonstrations of some additional components of CompuCell, focusing on compartmental cells and mechanical links to do junctional adhesion, solids, and other features of that kind. We'll also have a demonstration of how to use cell-to-cell contact signaling to do delta notch signaling and have a simplified model of the colonic crypt. So those will all be tomorrow. And we'll also have a little bit on programming practice. Giuliano will show you how to upload CompuCell simulations as NanoHub applications. And Jim Sluka will talk a little bit about best practice. And TJ will also talk a little bit about how to organize CompuCell simulations if you want to distribute them for other people to use. So with that, let's see if there are any other questions. Somebody said they asked a question in Slack and nobody answered. Why don't you ask it now so that we can figure that out? Probably somebody didn't catch that Slack thing. Okay. Well, we'll look forward to seeing you tomorrow morning. Thank you, everybody, for sticking it out. I know 4 consecutive days of 7 hours a day is a long day, especially for different time zones. We will continue to try to put the slide decks, exercises, and videos up as soon as we can. Thank you very much. Look forward to seeing you all tomorrow.